Thank you for that introduction. Hello, everyone, and thank you all for still being here. Is my screen visible right now? Because it's doing some weird stuff on my side.
I do not see it. I only see a circle.
Good. How about now?
I see it. Yes.
Okay, great. Cool. So in this talk, I will be talking about the primordial soup around SMM1-a, and that brings me to the context for this talk, which is very much about the origin of life, and that's one of my main scientific interests. My other scientific interest is chemistry. So what I am particularly curious about is where the molecular origin of life comes from. Now, we have a number of theories that you might have heard of, that the first building blocks of life are formed in this primordial soup on Earth, which is basically a pool of water with some molecules in there, which over time become more and more complex and eventually form an organism. Now, the aspect that I find interesting in this story is where do these first building blocks come from? And maybe there is a link with interstellar chemistry here, because maybe the molecules that are formed in space are being delivered by, for example, comets to newly formed planets and then help kickstart this early biochemistry. So what I do is try to determine which kind of molecular building blocks are available during star formation and can be used as planet building material. And I specifically look at a stage called the hot core, which is an early stage of protostar formation. And effectively, these hot cores are well known to have a large bubble of warm gas around them, which contains a lot of molecules. So this is a perfect stage for us to go look for molecules that might be related to life. And the type of molecules that I look for are not water. Although water comes from space, is very relevant for life, I look more at the organic species that are so-called prebiotic molecules, like the ones here. Now, these prebiotic molecules have one thing in common, that in a variety of reactions, they form biomolecules, such as amino acids and nucleobases. So I look for these prebiotic molecules to basically determine if they are available, and eventually they maybe lead to the formation of these biomolecules. And we look for these guys in this source called Serpens SMM1-a. And I already can give you a little bit of a spoiler. We detected all these molecules there. Now, we look at Serpens SMM1-a, which is an intermediate mass star. So as you might have guessed, it's right between high mass stars, which we traditionally have looked at for searching for chemicals in space, and the low mass stars, which are more like our sun. The nice thing about this intermediate mass star is that it's a little bit more luminous than a low mass star, so it's a little bit easier to detect chemical signatures from molecules, but structurally and physically they're less complex than these high mass star forming regions, which are further away and often contain multiple protostars. So SMM1 is a really nice source to look at. Next, what we do is we take ALMA and we observe a rotational spectrum of this source, and then we go look for rotational lines that belong to one of these prebiotic molecules, such as glycolonitrile, shown here. Now, the first thing we of course do is identify the transitions of this molecule, and then we start fitting this with a synthetic spectrum, which is here shown in blue. Now, this synthetic fit takes a couple of parameters, such as column density, excitation temperature, which will become somewhat relevant later on in this talk. Then we can fit these lines and securely identify the species. And one of the nice results that we got from these observations is the detection of glycolonitrile in SMM1, which is the first detection in SMM1, of course, but only the second detection ever in the interstellar medium of this molecule. Now, we do this for all the other molecules that I already introduced, and we basically find that surrounding SMM1, there is this very rich prebiotic soup of all kinds of prebiotic molecules, which, maybe with the help of comets, of course, can contribute to the emergence of life as soon as planets start forming around these objects. But yeah, being a chemist, I of course want to know more about the chemistry. So the next question obviously becomes, how is this prebiotic soup made? And I cannot cover all the material that we, all the information that we have gathered from our survey. But what I can give is a couple of examples of things we've learned about this prebiotic soup. Let's start with glycolonitrile, the molecule of which we only have 2 detections. But yeah, because we have 2 detections, we can start making some comparisons, which can already be interesting. The second detection of this molecule was towards a low mass star, Iris 16293b. And what I have done and shown here in this left plot is plotted the ratios of glycolonitrile with various other molecules. And what we very clearly see is that the ratio of glycolonitrile is a lot higher in SMM1 than in Iris 16293. Pretty much an order of magnitude higher. So this is quite substantial. Now, we still don't know a lot about the chemistry of glycolonitrile itself, but we can interpret this result already as evidence for some radiation-driven chemistry taking place in lukewarm ices that are surrounding SMM1. And this is based on the fact that SMM1 is much more luminous and probably irradiates its surroundings much more heavily than Iris 16293. Now, what I will also show in these slides, which I forgot to mention before, is actually a link to ALMA, what we will need from ALMA in future proposal rounds to further study prebiotic chemistry. And one of the things that we really need is larger spectral coverage of sources. To take the example of SMM1, I have now a number of molecules, which I've here plotted the ratios of, but that is all the molecules I got out of my observations. My observations covered only 1 gigahertz or so of bandwidth. So to really study the full chemical inventory, to discover more prebiotic species and to make more significant ratios, we really need to do broader bandwidth observations. Now, another thing that we can do is have a look at the origin of methyl isocyanate, which is this nice little molecule that you see here on the left. And since the first time it was discovered in the interstellar medium, it was already hypothesized that it is formed from or related to HNCO, which you see right next to it. And this is quite obvious because they are structurally quite similar. Now, first detection was in 2015, and now finally 5 years later, we have enough data points to make this nice plot, which you see here on the left-hand side, where we can plot the column density of CH3NCO with respect to HNCO, and we can actually visualize a trend between these 2 species. And we see that the ratio between these 2 molecules, the column density ratio, is quite uniform at about 10%, despite having a quite diverse set of sources ranging from very luminous high mass sources and very low luminosity low mass sources. And we interpret this as, first of all, a formational relationship between these 2 species. What the exact details are of that, that's still a little bit up for discussion. And this is already set at an early stage of star formation, probably in the dark cloud stage, and it takes place in the ice mantles on dust grains that are there. Now, the next thing that we need from ALMA is more large surveys and probably archive data to fill this plot here with much more data points. It has now taken us 5 years to fill this plot, and we can do that a lot quicker if we just get our big surveys going. And that will be really essential to study interstellar chemistry. Now, the final point comes a little bit from a different work of mine, but is still related to the SMM1 work, and that is the ratio of cyanamide and formamide, which we have plotted here in this graph for a variety of different sources. Now, one thing I want you to notice here is that the ratio of these 2 molecules differs quite substantially, over 3 orders of magnitude. And it seems to be actually mass or luminosity dependent as we go from low mass sources on the left to higher mass sources on the right. So this ratio steadily decreases as sources become more luminous or massive. And what we think that this does is basically give information about the thermal structure of a source. Because the one thing that you need to know here is that cyanamide has a very low desorption temperature, whereas formamide has a very high desorption temperature. And it could be the case that low mass sources simply do not heat their surroundings sufficiently enough to desorb all the formamide on the icy grains, but they can desorb cyanamide, and therefore you get a very high ratio. And for the high mass sources, they of course heat their surroundings, so that changes the ratio then. Now, what is interesting to test this theory is actually to use much higher spatial resolution observations of ALMA, because maybe we can look at, for example, SMM1 with very high resolution observations and see if we can see a variation in the cyanamide over formamide ratio as we go closer to the protostar. That will be very interesting to investigate. Now that brings me to the main takeaway message of my story here. The first one I want to say is prebiotic molecules are everywhere at the earliest stages of star formation. So they are so readily available that it becomes very likely that they indeed get incorporated in later stages of star formation in comets, and in one way or another actually end up on newly formed planets, where they help kickstart biochemistry, of course. The other thing is that to form this prebiotic soup, reactions in interstellar ice seem to play a very important role. But here in the category of prebiotic molecules, we are really only scratching the surface, and we are going to be using ALMA for a much longer time still to further our understanding of these reactions and to really understand how this chemistry comes to be. Now that brings me already to the end of this talk. Quickly, some acknowledgements. Here is the team that did the studies of SMM1. Special thanks to Aida Amari, who did a lot of great work on the data reduction. And a quick mention of the team of NGC 6334, which was my chemical clock story. These people were involved in that work. So with that, I want to thank you and invite you for some questions. And you can also contact me later if you have questions at later stages.